in this course for the PDEs. So firstly, just general differential equation, basically ordinary differential equation, not differential equation. Ordinary differential equation is given by f of t y dash y double dash plus into yn equals to 0. So this is the general definition of ordinary differential equation. So it will be linear if it will be written in this type. So basically the key points to note are, if there is no product term, there are no products of the function y of t, that is there should not be any yt into yt or something, and the highest power of yt should also be equals to 1. Also its all derivatives should be equals to 1. And if it is our differential equation, ordinary differential equation is not written in this form, then we'll say it is a non-linear differential equation, right? And the order, the highest, what is the order of differential equation? Ordinary differential equation, similar is the partial differential equation also. The highest order of the derivative, which is the highest order derivative occurring in the equation, is called the order. And the highest, the power of the highest derivative, if we write it in the polynomial form, then the highest order derivative, the power of that highest order derivative is called the degree of the differential equation, right? So basically we can, now coming to the PDE side, basically we'll discuss mainly for the PDE. So first order PDE in general, the first order PDE is given as f of x comma y comma z p comma q equals to 0, where p is equal to del z upon del x and q is equals to del z upon del y, where z is the dependent variable. We have a dependent variable z, which is depending on my two independent variables x and y. Here x and y are two independent variables. Sorry, the first order for the dependent variable, and these x and y are independent variables, is given as f of x y z p comma q equals to 0, where p is equal to del z upon del x and q is equals to del z upon del y. Now using, we can classify our linear differential equation into three types. First is the linear case. In the linear case, in the product of p also there should not be z term. So the coefficient of p should be function of x and y. Similarly, coefficient of q should also be function of x and y. Coefficient of z, there should be a z term with coefficient in x comma y plus some terms of r x comma y, that is z should appear also linearly in this case, then it is called purely linear differential equation. Second, it is called semi-linear if the right hand side is a function of x y z, and on the left hand side product of coefficient of p should be x and y, and coefficient of q also should be some function of x and y. And it is called quasi-linear if we have on the p or q product is of the form xyz, and also the product of q is of the form xyz, then in this case we call quasi-linear. Otherwise there is some power of p. Whenever I say p and q, I am referring to small p and q. If there is power of pq, product of pq, or any such thing, it is involved in some function, in that case we'll say differential equation is non-linear. Now based on whether the equation is linear or non-linear, we have different methods to solve that. First, for the linear differential equation, which is popularly known as Lagrangian method. In that method, what we'll do, we'll first write our differential equation in the standard form pp plus qq equals to r, which is this form basically. So we'll try to find solution, general solution given by phi of u comma v equals to 0, where u of x y z equal to some constant c1 and v of x comma y comma z equals to c2. So what we will do, we will write our the equation in standard form p plus qq equals to r. Then we write it the Lagrangian equation, which is given by dx upon p dy upon q equals to dy upon z. Now we have to make a combination such that we can find two linearly independent solutions, like we did in the different questions that we have tried. We can find the, like sometimes it is easy, that is in the separable form only. So as we have to find some combination like p plus q plus r, or p into x into, or like some this kind of things like dx plus dy plus dz over p plus q plus r equals to 0, or sometimes we have to multiply with x dx plus y dy plus z dz upon xp plus yq plus z are equals to 0. In this case, sometimes we have to divide or we have to find the possible two linearly independent solution we have to find for this equation. So this is for the linear case. Also there is a Cauchy method, and that will see this kind of similar things, but this is equals to some dt in that case, and we can write it in the parametric form. There will be initial data also given, so we can write it in the parametric form and find the corresponding solution. Now there are different kind of solution. One is called complete integral. The complete integral is given by phi of x y z a b. So this kind of solution of a PDE, phi of x comma y comma a b, this will give rise to a first order differential equation that you can form from this. And also the solution can be written in this form, or you can also write in the form of f of u comma v equals to 0. Now a two parametric family of solution which is represented as z is equals to f of x comma y comma a comma b is called complete integral if the rank of this matrix M matrix is 2. Then we say that solution is complete. And there's one more solution which is called singular solution, which cannot be obtained from the general solution by substituting the values of constants. That solution is called singular solution, and which is given by here. We can find it by differentiating the constants with respect to constant and substituting to 0, and substituting back the value of finding the value of a comma b, we can get the solution. That solution is called singular solution. Basically by finding the envelopes, by this way we can find the envelopes of the equation. So using that we can find the singular solution. Now coming to the non-linear differential equation side, in that case first we'll discuss the compatibility condition. What is compatibility condition? We say that two PDEs, let's say we have two PDEs, fx comma f and g. So these two differential equations, these are two different non-linear differential equations. They are said to be compatible if they have a common solution. If they have a common solution, we say that yes, these two PDEs are compatible. And to check the mathematical equivalence of checking compatibility condition is box of f comma g should be equals to 0. Where what is this box of f comma g? This is equals to Jacobian of fg upon xp plus del fg upon del yq plus p del fg upon del zp plus q del fg upon del zq. If this box is equals to 0, then we say that f and g are compatible. Where what is this kind of terms? This kind of terms del fg comma del fp. This is basically the discriminant of this term. GFP, sorry, FP, GP, GQ. So determinant of this is given. This is the determinant of this thing, right? Now using the compatibility condition, what we are saying, if we can find a solution, f and g will have a common solution. Using this, we can find the solution of non-linear differential equation. Let's say we are having a non-linear differential equation f x y z p comma q. So what we'll do, we'll first find f of x, f of y, f of z, f of p, f of q. We'll find all the corresponding partial derivatives, and we'll write it in the we'll write the auxiliary equation. Write the auxiliary equation as dx upon fp. This is the auxiliary equation. This method is called Charpit's method. So what we'll do, we'll try to solve up equation in terms of P and Q. Basically what we'll do then, we'll find one solution, one parametric family solution, g x y z comma a. Since we are solving a differential equation, so there will be a constant also. So what we'll try to write P in terms of x y z, q in terms of x y z. So this is our motive. We have to write express p in basically this g, this g, this charpit the auxiliary equation comes from using this equation, this compatibility condition. So g and f are compatible. So if they are compatible, so we can write p in terms of xyz and q in terms of xi xyz. So if we can write this, then we can solve this differential equation. Dz is equals to phi dx plus xi dy. So using this equation, we can find the solution. We have done different examples also in the class. So there are special cases of the Charpit method. First thing is when f of p comma q is equals to 0. If f of p comma q is equals to 0, then we can take p is equals to a and q is equals to phi of a. So we can substitute here that dz is equals to a dx plus phi of a dy. Second case is, if we have p f of p q z is equals to 0, then we can take p is equals to aq, and then q will be equals to some xi of a comma z. That is, we'll substitute in this equation p is equals to aq, and we'll get that q is equals to xi a comma z. We'll get q in terms of a and z, and we can substitute again here, then we can get the corresponding solution. Third type is if it is in the separable form, that is f of x y z p comma q. There is no z term. This is written as some function of g of x comma p minus h of y comma q. If we separate the xp and yq terms, then we can take the solution, that is g of x comma p is equals to h of y comma q, which is equals to some constant a. So using g we can write p in terms of x. Using these two equations we can write q in terms of y. So we can substitute here and again solve to get the answer. Fourth special type is called Claret solution. This kind of things also occur in the differential equation. So in this case we have this particular form, z is equals to px plus qy plus some function of p comma q. Then the Claret solution is given as z is equals to ax plus by plus g of a comma b. That is, we'll substitute p equals to a and q equals to b. So this is what we did for the first order differential equation. Now coming to second order partial differential equations, we'll use the following notation for the second order differential equation. R is equals to del z upon del x square, s is equals to del square z upon del x del y, and t is equals to del square z upon del y square. So this is the notation that we are going to use. So the standard general second order differential equation is given by RR plus SS plus TT plus f of x y z p comma q equals to 0. Right? Now let I am denoting delta by s square minus 4rt. This is of interest to me. Let this is be delta. Now we can classify the second order differential equation into three types: hyperbolic, parabolic, and elliptic PDEs. Now if this delta is strictly greater than 0, then we say it is hyperbolic, and in that case we have two real characteristics. I'll come to that what are two real characteristics. And if delta is equals to 0, then we say that our differential equation is parabolic and that have one real characteristic. And if delta is strictly negative, then we say that it is an elliptic differential equation and have zero real characteristic. There will be some imaginary characteristics but not no real characteristic. So basically these characteristics are useful in solving directly this equation is very difficult. So what we do, we'll transform the different differential equations depending on their classification to their canonical forms. Canonical forms are just an improved version of this differential equation which are comparatively easier to solve. So to convert that we need these things what are called the characteristics. Basically we are going to solve this differential equation r lambda square plus s lambda plus t. This will give me the value of the characteristic. How? And the discriminant of this is b square minus 4ac, that is s square minus 4rt, right? So this discriminant is s square minus 4rt. Now it will be positive, then we'll have two real roots. So in that case characteristics will be given by, to find the characteristics we have to solve this differential equation y dash plus lambda equals to 0, right? In case of hyperbolic we will have two characteristics, so we'll get two equations, y dash plus lambda 1 equals to 0 comma y dash plus lambda 2 equals to 0. And in case of parabola, s square minus 4rt will be equals to 0, so we'll have only one root, so the characteristic will be solved by y dash plus lambda equals to 0. And second characteristic we can choose such that it is linearly independent of first. And similarly in the elliptic case we can choose from the corresponding to imaginary solutions. We can take one solution and other linearly independent solutions, right? And the canonical form, standard type of canonical forms is, in the terms of hyperbolic PD, the equation is getting converted into this form or this form. These are the two specific forms in which equation get transformed. And in the for the case of parabolic equation we'll get this. These are the two quantities that we get. So basically it is easy to solve. Let's say if all other terms are 0, only is u let's say u eta eta equals to u xi is there, then we can solve easily using the separation of variable or just integrating. And canonical form for the elliptic PDE is given by this term. So these are the different things that we have. Now coming to the particular equations, first let us discuss the elliptic equations or the Laplace equations. Elliptic equation are also called, one of the primary example of elliptic equation is the Laplace equation given by del nabla square u equals to 0 or del u equals to 0. So this is the elliptic equation, and we can write different versions of this in the polar coordinate system. If we take x is equals to r cos theta, y is equals to r sin theta, such that r square is equal to x square plus y square and theta is equal to tan inverse y by x. In this case, this is the equation corresponding to polar coordinates. And if in the 3-dimension case, that is where this del square is equals to del u upon del x1 square plus del u upon del x2 square. And depending on the dimension, if it is 2 dimension, then only 2 terms. If it is 3 dimension, then it will be third term also, del square u upon del x3 square equals to 0, right? So in the cylindrical coordinates, what do we have? X equals to r cos theta, y is equal to r sin theta, z equals to z. So in that case, this is the corresponding cylindrical equation, Laplace equation in cylindrical form. And in the spherical coordinate system, we can take x equals to r cos theta cos phi. We should write it here. X equals to r cos theta sin phi. Y is equal to, sorry, cos phi it is. Y is equal to r sin theta sin phi. And so just in the spherical coordinates, we can write x is equal to r cos theta cos phi, y is equal to r sin theta cos phi, and z is equals to r cos phi. I'll write it here. And in that case, the equation is given by either this form, and if you expand this using the product rule of derivatives, then you get this equation, right? So these are the different versions of Laplace equation. Now the solution of the Laplace equation depends not only on the problem but also what are the conditions that are given to us. So that conditions are also very important. So let's say we are solving Dirichlet problem for a rectangle. So in that case, we'll have del square u equals to 0, x is between 0 to a and y is between 0 to b. So that is a rectangle of length a and width b. So in that case, we are having the boundary condition as u of x comma b is equals to u of a comma y equals to 0, which is homogeneous, and u of 0 comma y equals to 0, u of x comma 0 equals to some f of x. So let's say we want to find the solution inside the rectangle. So in this case, the solution is given by u of x comma. This is a solution where the coefficient a comma n, where the coefficient a n is given by 2 upon a 1 upon sine hyperbolic, where sine hyperbolic is a hyperbolic function e raised to power x minus e raised to power minus x by 2, and this is equals to 0 to a f of x, where f of x is this f of x sine n pi x upon a dx. So this is the solution. So here we were given the Dirichlet boundary condition. So we are given data on the boundary. Now let's say we are not given the data on the boundary, but we are given the information about its derivative on the boundary. So in that case, what we'll do, we'll have the solution is given as u is equals to, that is u of x 0 comma y is equals to u of x a comma y equals to 0, u of y x comma 0 is equal to 0, u of y x comma b equals to f of x, right? In that case, the solution is given by u is equals to a naught plus summation n equals to 1 to infinity a n cos n pi x upon a cos hyperbolic n pi y upon a, where a n is given by, this is small a n is given by 2 upon n pi 1 upon sine hyperbolic n pi b upon a 0 to f of x cos n pi x upon a dx. So this is the problem for the Newman problem on a rectangle. Now if we are talking about the circle, so basically in the circle, to solve these solutions are obtained. First thing, these solutions we can obtain using the various variable separable forms. That is, we can write our solution use x comma y is equals to x of x y comma y. Then you will get some separable equations like of the form x double dash upon x is equals to y double dash upon y, and you can assume it to be constant, let's say lambda. Then you have to discuss three cases when lambda equals to 0, lambda positive, and lambda negative. In that case you will find the eigenvalues. In which case you are getting eigenvalues, that case you will get the non-trivial solution, and that solutions are basically I am writing it here. And we are also using in between the orthogonality of sine pi x, sine n pi, as well as sine hyperbolic n pi's. Now for the, if we are going to solve the problem on a circle, then in this kind of situation our polar form will be used basically, because on the circle boundary is also circle, so it is easy to implement it on the polar equation. So we can convert that into polar equation, and if let's say boundary conditions are given to be, so r is between 0 to 2 and theta is between 0 to 2 pi. Let's say u of a comma theta is equals to f of theta. Then my solution, this is interior of the circle, so in the circle the solution is given by this formula, and this is called the Poisson integral formula for circle, where a square r square is known, f is known, we just have to find the integration of this function. And if the problem is about to find the solution outside of the circle, this part outside of the circle, but there should be a condition that u must be bounded as r, as the radius tends to infinity, then the solution u of x is given by this formula, right? So similarly, for Laplace equation for the cylindrical coordinate system, if we have a cylindrical coordinate system, then the general solution u of r comma theta will be equals to jn of lambda r c1 e raised to power lambda z plus c2 e raised to power minus lambda z, c3 cos n theta plus c4 sin n theta, where this jn is the first order Bessel's polynomial, which I have already told you guys. And the solution of the Laplace equation in the spherical coordinate system will be given by this, where p uh, this spherical coordinate system, and in the spherical coordinate system we are assuming the coaxial symmetry to be equal to 0, so the term corresponding to del u upon del phi will be equals to 0, and in that case the solution u of r comma theta will be given by this, where pn and qn are the Legender's polynomial, first order and second order Legendre polynomial, which we have already discussed in the class, I guess 10th class, 10th and 11th both. And we have also given some of the recurrence relation that are useful in that problem. Also the orthogonality property, which is very important for the Legendre as well as Bessel's polynomial. For Legendre polynomial it is corresponding to weight 1, and in Bessel's polynomial it is corresponding to the weight x. So this is the cases of Laplace equation. However, in the case of heat equation, let's say we are having our equation del u upon del t is equals to alpha del square u upon del x square on minus infinity to infinity, and u of x comma 0 is equals to fx on minus infinity to infinity. Then u of xt will be given by this equation. This is the same formula that we have used in the last question in today's lecture. And for the finite case, in the case of a finite rod case, let's say we have 0 to x to L, and u on the boundary we are given the data to be 0 and u of x comma 0 equals to f of x, then u of xt is equals to given by this equation, in which a of n is equals to 2 upon L 0 to L f of x sine n pi x upon L dx. This is the question. This is similar to the first question that we have discussed in the today's lecture. Now again, in the case of infinite rod with data u of x comma 0 equal to u naught for a to b and 0 otherwise, then the solution u of x comma t will be given by u naught upon t erf b minus x upon 2 root alpha t minus erf a minus x upon 2 root alpha t, where erf of z is given by erf of z is equals to 2 upon root pi 0 to z e raised to power minus t square dt. Now for the corresponding to the non-homogeneous equation, if we have the non-homogeneous equation in the case of infinite case, I am saying, u of x comma 0 equals to 0 is given, only the equation is non-homogeneous, initial data is 0, then in this case the solution is given by this equation. And for the non-homogeneous heat equation with non-homogeneous boundary data, let's say ut is equals to u of xs plus f of x, u of 0 comma t equals to h1, u of l comma t equals to h2. Let f cap of f of x comma t is given by this equation. Then u of xt is given by summation n equals to 1 to infinity a n r e raised to power minus n pi l square tr uh, sine n pi x upon l d tau. This is variable, and where a n tau is equals to 0 to l f cap xr sine n pi x upon l dx. This is the one question, that second last question that we have discussed in the today's class. Then corresponding to the wave equation, for the fund dimension wave equation, we have the D'Alembert's formula, which is given by, let's say we are having a wave equation on the infinite with infinite string case, and it is given with u of x comma 0 is given to be f of x, ut of x comma 0 is given to be g of x. Then in that case the solution is given by this. However, for the finite, if we are taking semi-infinite length, that is we are taking here to be 0 fixed and here infinity, in that case our solution u of x comma 0 is equals to f of x, ut x comma 0 is given to be g of x. Then what we can write? We can write the solution in this form: u of x comma t is equals to half capital F of x minus ct, where capital F and small f are defined as f of x is equal to f of x for x positive, and in the negative part we are taking minus of f of minus x. Similarly for the g of x case. So in the case of vibration of an infinite string, it is defined as follow. And for a finite string, if we have a length 0 to L, in that case with the similar assumption on the boundary conditions, then the solution is given by this, where f of m is equals to 2 upon L, 0 to L, f of s sine m pi s L ds, and g of m is given by this. It will be g of s only, not f will not be there. G of s sine m pi s L ds. And finally, for the wave equation in the two dimension case is given as, in the two dimension case, let's say ut equal to u of xx plus u of yy, u of 0 comma y comma t, and this is equals, this is the condition, and u of x comma y comma 0 is equal to f, and ut of x comma y comma 0 equals to g. Then this is the solution where r is given by this, amn is given by this formula, and bmn is given by this formula. So finally, using the Duhamel's principle, if we are solving utt minus c square u of xx f of xt for the infinite case, u of x comma 0 f ut x comma 0 equal to u of x, using Duhamel's problem, we have u of x is equal to half x plus ct plus half x minus ct plus 1 upon 2c x minus ct x plus ct g of s ds plus 1 upon 2c 0 to t x minus c t minus tau x plus c t minus tau f of s comma tau ds dt. So these are the some formula sets that we have been using throughout our course for the partial differential equation case.